This screencast is on atomic orbitals and quantum numbers. Atomic orbitals are the region in space where there's a high chance of finding an electron. Remember that electrons spin really quickly around the nucleus, and so we don't find them in just any one particular location, but we find them in a region or a general area in the atom. And so we're going to take a look at those different areas where we're likely to find an electron. The first orbital is called the s orbital, and it is shaped like a sphere, which we see in the diagram here. Remember, the atom is not one-dimensional, it's three-dimensional, and so we're not looking at a circle, but more of like a ball shape, where the electron is going to be spinning very quickly around the nucleus of the atom. The p orbital is a little more complicated. It's called a dumbbell shape, and you can see that it happens on three axes, the x-axis, the y-axis, and the z-axis. So all three of these axes are put together, and we'll find that the electrons are spinning in one of these bubble areas around the nucleus. Next is the d orbital, which just adds even more dumbbells into what we had for the p orbital. It's a little more complex, can hold a little more electrons, but again, these shaded areas are the region around the nucleus where we're likely to find an electron. The last orbital shape is called the f orbital, and again, we see that there are even more bubbles here, more dumbbells, and so again, more areas where the electron can be spinning around the nucleus of the atom. So what exactly is a quantum number? Well, a quantum number describes where the last electron is located, the outermost electron, that one that's farthest away from the nucleus in the atom. You kind of think of it like the address for the electron. Each element on the periodic table will have a unique quantum number, and this follows the Pauli exclusion principle. For example, hydrogen's quantum number would be 1001/2. Let's take a look at how we determine the quantum numbers for elements. Before we get started, we need to move helium from the right-hand side of the periodic table over to the left-hand side, as you see in this diagram. Helium is a noble gas, which is why it's in that far right-hand column. However, when we're looking at the electrons and atoms, helium fits in a little bit better on the other side of the periodic table. So if you're taking notes on a periodic table, please go ahead and move helium over where you see it on this diagram. The first number in the quantum number is called the principal quantum number. It's also labeled the N number, and this describes the energy level of the electron. This corresponds to the row number that the element is in on the periodic table. And I know this doesn't make a whole lot of sense right now, but what I want you to know is that in the D section of the periodic table, we take the row number the element is in and subtract 1. And in the F section of the periodic table, we take the row number the element is in and subtract 2. For now, just keep those two little pieces of information in the back of your mind. It will become a little more clear here in just a few moments. So here's a diagram showing the principal quantum numbers. Again, if you're following along with your own periodic table, on the left-hand side, please write down the row numbers 1 through 7 like you see in red. Note that the two rows at the bottom of the periodic table are actually part of row number 6 and row number 7. In that middle section of the periodic table, okay, right in here, where we see it kind of dips down a little bit, I want you to write row -1. Where I said in the previous area where we take the D section, we take our row -1, this is where that happens. So let's look at an example. Iron is in row number 4, okay? But if I were to figure out the principal quantum number for iron, I would take my row number, which is 4, minus 1, which is 3. So my principal quantum number for iron is actually 3. Down here is the F section. These two rows at the bottom are the F section. Okay, and that's where we take our row number -1. So for example, uranium is in row number 7. If I wanted to find the principal quantum number, I would take 7 minus 2 to get a principal quantum number of uranium of 5. The second part of a quantum number is the orbital quantum number, or the L number. This describes the shape of the orbital. Remember those shapes, spheres, and dumbbells that we were talking about earlier, the S, P, D, and F orbital? Well, here's where they come into play. These are going to be assigned areas on the periodic table that describe those regions where we're highly likely to find an electron. And here we see those different regions. you're going to color your periodic table in a similar fashion to this. It doesn't have to be the same colors, but use the same schematic. So this first section here, these first two columns on the periodic table, any element that is in those two columns has electrons in the s orbital. Okay, s is given the number 0, and we see that here. So s equals 0. Over here on the right-hand side, with these blocks that are all shaded a bluish-purple color, that's the p block of the periodic table. The electrons that are represented by those elements are in that p orbital, and p is given the number 1. So what I want you to do is color your periodic table and write p equals 1. In the middle section of the periodic table, where it's colored this yellow shade of color, this is the d orbital. Okay, so color that section of the periodic table, and then I want you to write above it d equals 2. And finally, these bottom two rows that are shaded green here, this is the F section, or the F block of the periodic table. I want you to label that F equals 3. So what we're doing here is we're simply looking for where does that block fit in our color-coded scheme of the periodic table. For example, if we were looking at this block, that fits in the D section, so our orbital number would be 2. If we were looking at this block, it fits into the F orbital section, so our orbital quantum number would be 3. If we were looking at this element, it's in the P section, so our orbital quantum number would be 1. And if we were looking over here, in the S section, our orbital quantum number would be 0. The third part of the quantum number is the magnetic quantum number, or the M number. This describes the electron's orientation in space. This will play a bigger part when we get to writing out orbital filling diagrams, but for now, just know that there's a certain order that electrons fill in the orbital, and this number indicates where those electrons are located. On your periodic table, I want you to write the numbers at the top of each column as you see with this example. These are your magnetic numbers. So for example, we have 0, 0, -1, 0, 1, -1, 0, 1, -2 through +2, -2 through +2, and then -3 through +3. And we repeat with -3 through +3. The way the magnetic quantum number works is whatever column the element is in, that's the magnetic number. If we were looking at germanium, the magnetic number would be 0 because that's the number at the top of the column. For platinum, our magnetic number would be 0 because that's the number at the top of the column. What would the number be for iron? The correct answer is -2. What about xenon? Our magnetic quantum number would be 1. The final part of the quantum number is the spin quantum number, and this is also referred to as the S number. This indicates the direction of electron spin. Two electrons can fit in a seat together, but they spin in opposite directions. One spins clockwise and the other one spins counterclockwise. For the quantum numbers, we indicate this with either a +1/2 or a -1/2. Notice that -1/2 is the first half through the range on the periodic table, and -1/2 is the second time through your range. On your periodic table, you should have the magnetic numbers written at the top of each column. Bracket off the first time you go through those numbers and indicate that as a -1/2 spin, and the second time you go through those numbers, indicate that as a +1/2 spin. Again, based strictly on where the element is located on the periodic table, that determines the spin. Here's palladium. Palladium is in this bracket, so it has a +1/2 spin. Silicon is in the first bracket, so it has a -1/2 spin. What would the spin number be for magnesium? +1/2. And what would the spin number be for uranium? -1/2. Write the 4-digit quantum number for potassium, tungsten, and copper. Remember, if you're dealing with the principal quantum number, to take your row number -1 if you're in the D section, and your row number -2 if you're in the F section. Write the 4-digit quantum number on a piece of paper, take a picture, and upload your answers into Schoology.